Okay, hello everyone. I'm going to go ahead and get started. My name is Tyler Wiggins. I am the engineering manager here at Everest Solar Systems, and today going to be talking about ways that you guys can maximize module density on commercial flat roofs. So I'll go ahead and get started. So today we're going to talk about three main things. First off, I'll give you guys a brief introduction of our company. Next, we'll talk about some of the advantages and disadvantages of south versus east-west systems, or want to think about it as a single tilt versus a dual tilt system. And then last, we'll get into basically some ways you can maximize module density using our system called DDome Rsquared. So Everest Solar Systems really began as a sister company to K2 Solar Systems, which is located in Germany. They have offices in the UK, France, Italy, as well as opening some in Brazil and South Africa. Everest is located in Oceanside, California, and we also have an office in Mexico that serves our customers in Mexico. We have a worldwide presence with a little over 5 gigawatts installed in a little over 100 countries. This list is constantly growing as a lot of countries are looking towards using solar to handle their electrical needs. We have a lot of distributors located all over the United States. As you can see, the majority are in California and New England, but we are getting more and more as more central states are looking toward solar to help them with electrical needs. So I'm going to start off talking about traditional south-facing systems. I know these ones are systems that a lot of our customers are familiar with. Definitely would call this more traditional in a sense that, facing your solar panels south, you're definitely going to get maximize your output per solar cell or per panel. So these systems have been around for a long time. They have a lot of great advantages with regard to, as I mentioned, productivity. Produce a lot of power facing them south, and also have some advantages with regard to servicing and stringing. Since all these panels are facing the same direction, it doesn't create a lot of complications with stringing the modules. And since there is that inter-row spacing, it gives a nice aisle for serviceability. But they do have some disadvantages, particularly if we're talking about roofs that have a lot of obstructions, or ones that the roof is not big enough to handle the needs of the building business that is requiring more electricity than the roof can offer with a south-facing system. So some of those disadvantages being inter-row spacing. So we talked about in the previous slide, the inter-row spacing is beneficial for servicing, but it's creating what's basically dead space on the roof where we're not putting any modules. Another disadvantage of these systems is that because of their geometry, they either require a windscreen or they're open on the back, which creates higher loads on the panels under a wind event. So if we're looking at ballasted systems, these south-facing systems typically have a high average PSF. They end up being heavy. So if there's certain roofs that say the max they can hold is 4 or 5 PSF, if it's a tall building, it might be difficult to put a south-facing system on the roof just because the system is too heavy. So you do have the option of anchoring, but there are cases where the roofing manufacturer may not allow anchoring with fears of water intrusion and things like that. So as I stated before, inter-row spacing, sure, a lot of you are familiar with this, is really we're just making sure that we're not getting any shading on the panels, as you can see in this diagram here. So, particularly if we're talking about the difference between a south-facing system in, say, Southern California versus New England, This inter-row spacing is going to change based off that angle of the sun at different times of the year, based off the latitude of where we are in the U.S. or really anywhere around the world. So we can definitely see some disadvantages with this inter-row spacing in, say, a place like Massachusetts versus maybe Southern California. So at this point, I'm going to talk to some points discussing module density. So we'll look at a really simple example here. If we have a 30 by 30 foot roof, it's pretty small, but it works well for this example. We look at a south-facing system. We'll just assume that it's 10-degree tilt, and we're looking at about 1 foot of inter-row spacing here to deal with that shading we discussed in the previous slide. So with this example, we got 6 rows of panels, 5 modules in each row. It gives us 30 modules on the roof. If each one of these modules is 300 watts, at 30 panels, we're looking at 9,000 watts total on this roof. Because we have that 1 foot gap and it's 30 feet wide roof, we're looking at 30 square feet of unused space in those aisles for that inter-row spacing, which gives us a grand total of 150 square feet of unused space. So there's definitely some room for improvement there. If we look at a dual row tilted system or an east-west system, we're able to fit significantly more panels on this roof because we don't have to deal with that inter-row spacing. So now we're looking at 4 rows of 10 modules or 40 modules total. At 300 watts a module, 40 modules, we're looking at 12,000 watts now, and a very low square footage of unused space because now we don't have those inter-row spacing in those aisles anymore. So now I'm going to speak to our system called DDome Rsquared. I'll go over the components. I'll talk about how the system is ballasted, also has the option of being anchored, and then as well as the fixed 10-degree pitch and some other benefits of this system. There's a basic overview. As you can see, it has the option to be ballasted. Where that ballast tray is, it also has the option of being anchored. Just to give an example of where this product has been used in the past, this is a Harmon's grocery store located in Utah. In this particular project, this building had a very high demands for electricity for their freezers and everything else. A traditional south-facing system was not able to meet their needs based off of their production that they were looking at, so they opted for an east-west system to give them a much higher density. As you can see in this example, they packed this roof with as many modules as they possibly could. There's very few spaces that don't have solar panels on it. I'll talk about some benefits of DDome Rsquared at this time. The first off being this system typically has very low ballast compared to a south-facing system. So the reason for that being is that because of the geometry of it, that triangular shape on the geometry, it does not have a wind deflector on it. The loading overall in the system is much lower than what we would see typically with a south-facing system. And because of that, we're able to see much lower loads on the roof due to the ballast than a traditional south-facing system. Again, as I mentioned before, because we don't have that inter-row spacing, we're able to see a much higher module density, able to fit panels where normally we would have a service aisle or a space to prevent shading. This system is listed with UL, and each subarray only requires 2 grounding lugs because the system is listed with the clamps as well as the other components on it. All these components are modular, very small, packed very easy into crate for shipping, and also just have a very low part count. We're looking at 5 standard parts with this system. So at this point, I will go over the components. I'll start with what I consider the main component here, which is called the peak, the dome peak. So with this component, here's the module landing area. This is also where the clamp is inserted. It uses the same geometry as our rail components, if you're familiar with our residential systems. It has the same T-bolt channel that our rail components have, and this is where we would add a microinverter mounting bracket as well as wire management options. And this tab down here is for the corner strut and porter, which I will go into more detail in later slides. So I get this question a lot, so I wanted to cover it now. This system has a fixed 10-degree tilt. We get questions sometimes if there's options to go to a 5-degree or lower. At this time, we only offer fixed 10-degree tilt. Next component is the base. Located here. So with this component, just like our peak, we're looking at about 3 1/4 inch in-row spacing between the panels here. The modular landing area, very similar to the peak, the same geometries with the rail with regard to clamping. And this part on the side of it is the corner strut attachment slot. So that is where we're going to attach the corner strut. Talk about that component right now. So with this component, with some of our customers, there's some confusion about where it needs to go, and it really comes down to each specific installation because depending on loading conditions, wind conditions, the weight or the ballast required for each system is going to be very dependent project to project. So with this component, it goes on the corner of every subarray, and it's used to reinforce the corner of the array, since at the corner is where we're going to see the highest wind loading. This is one of the very few components in the system that requires hardware. It's a bolt and a nut that goes in and attaches it to the base, and it's compatible with 60, 72, and 96 cell modules. So another benefit of this component is if you're dealing with a system that's, say, in an area that has high wind loading, like, say, Hawaii or eastern parts of the United States that are along the coast that dealing with hurricane force winds. What this component allows you to do is to add more ballast than what we would typically see. So as you can see in this picture here, we're able to fit a significant amount of ballast blocks using that corner strut component. So the last piece of the puzzle, if you want to call it that, is our porter tray. So as I mentioned before, this is where the pavers go, where the ballast block goes. And in the previous picture, we showed it on the corner strut. It can also go in between the peak components. Depending on the module you're using, you're able to fit anywhere from 3 to 4 standard 32-pound blocks, which are 4 by 8 by 16 dimensions. So as mentioned before, this is compatible with 60, 72, and 96 cell modules. And this component, unlike the corner strut, does not have any hardware. The porters fit right on the slot of the peak as well as the corner strut component. So I wanted to show you guys another example of where DDome Rsquared can be used to maximize module density. Here's an example of Stone Brewing Company. They're based out of Escondido. With this particular project, they again had some higher needs for energy production. So opted for an east-west system, really to maximize the amount of modules they could fit on the roof. I do like the way that this system looks because it really shows off how sleek the system can look if you have a lot of obstructions on the roof. Again, dealing with these skylights, as you can see, you're able to fit a lot of modules in between those gaps where it might be more difficult with other types of systems. The last thing I wanted to talk with you guys about today is our DDome Rsquared Base-On tool. So this is a tool that we have that's able to help our customers design their own systems, calculate their ballast, generate their reports for their engineers, as well as print their bill of materials so they can take those to their distributors and get a quotation on how much a system is going to cost to install the materials. So this is located on our website. It's free to use. All you have to do is sign up, give some very basic information, and I'll get you approved and be good to go. This is very similar to other design tools out there. We're basically drawing the roof on top of Google imagery and then placing the modules on top of that. So if anyone's interested, next month we'll be giving a webinar. It'll probably be longer than our typical 25-minute webinar. We'll be going through a couple examples with this tool, going into some more detail about a little more in depth on how it's used. If anyone can't wait and they'd like to have some training done before, please just let someone in inside sales know. I'll provide an email at the end of this webinar. So as I mentioned before, once you have the design laid out, the ballast plan, it'll give you a list of materials, and then this can be printed out and taken to a distributor for a quotation. So just to kind of recap on what we talked about today, we talked about traditional south-facing systems, how they have some advantages and disadvantages, particularly with inter-row spacing, and how we've taken advantage of that with our DDome Rsquared system, where we don't have as much inter-row spacing as you'd see in a traditional south-facing system. I talked about our components, the component count, where those components go and why they're there. And then last, we discussed the DDome BaseCamp tool, where you guys can find that and how it can be used to help you build your systems. If you have any questions, the person you want to speak with, his name is Ulysses, and this is his email here. He's in our inside sales team. If you have any questions about capabilities of the systems, or if you'd like to get help getting something designed and quoted, he's definitely the person who can help you out. I want to say thanks a lot for joining me with this webinar today. At this point in time, I'll leave it open to any questions. Feel free to type them into the user interface you have with GoToWebinar, and I'll be on for the next couple minutes to answer any of them. If you have any questions specific to engineering, please feel free to email Ulysses about them, and he'll forward them on to me, and I'd be happy to speak with you. Thank you very much, and I'll stay on, see if we have any questions today.